Welcome to After Hours Engineering, episode 11. We've reached the bit swizzling episodes. Sounds strange for sure, but the branch and the jump instructions immediate fields are constructed via bit swizzling. Now, having said that, we'll start with the I-type jump and link register instruction, which actually doesn't do any bit swizzling. However, its counterpart, the JAL, does use bit swizzling, and we'll be introducing ourselves to swizzling via that instruction. However, manually bit swizzling is very error prone, and as such, I built a one-line or a single-line assembler that should help us minimize errors. However, as I was recording this series, Bruno Levy came out with this very cool and clever inline assembler in Verilog. So links below to that if you're interested in embedding inline assembler with your Verilog. It's really cool. And finally, we cover the S and the B type, the store and the branch type instructions. So let's jump right in. As usual, we start with the data flow diagram and then update our FSM with the new state flows. Because we're doing the JALR, we have two things that we need to do. We need to load the program counter with the target address of where we're going to jump to, and we need to load the destination register with the next instruction to be read. That would be the return address. So we'll do the first one first. We'll start by loading the PC first. So in order to do that, we need to take the contents of RS1, route it through here, and our immediate, which is in the instruction itself, and route that over through here. We need to add those two together and then route it all the way back and into the program counter so that on the next clock it's loaded into the PC. Now that calculates the target address. We now want to calculate the return address that'll be stored in the destination register. So to do that, we grab the contents of PC prior, which has the current address of the instruction itself, and we need to add 4 to it. So we'll route the PC prior here. We'll grab the constant 4 and we'll add them together and then route them back in for a write back and store it into the destination register. Here we are at the FSM, and I'll go ahead and turn on the new pathway. You can see that we will update the decode statement to set the new pathway so that it comes down and runs this section right here. Again, we saw on the data flow diagram that we needed to set the RS1 or RSA on my channel, the immediate, which is embedded in the instruction, and then the target, which comes from the output of the ALU immediate directly into the program counter register, and then we set it up for load. Now the one additional thing we do is we check to see if the destination register is X0. If it is, then it turns out this instruction is nothing more than just a pure jump instruction. It is not a jump and return type of instruction. Otherwise, we come down here and we set up to grab the return address, which is again using the PC prior. We're adding 4 to it, and we're setting and routing the data into the register file with these two signals right here. And this is the JALR instruction. Now we take a look at the HDL code to back up that FSM, and here we are at the control matrix. I've added a new case statement to handle the new pathway in our FSM, and it's right here below the last one that we did. So with that added in, we can now venture on down here to the instruction, the JTJALR instruction. And as you can see, we are setting up our two sources, RS1, the immediate. We're setting up the routing into the program counter with the ALU immediate output, and we're enabling loading. We're also looking to see if the destination was the X0 register. If it is, then we just immediately go to the fetch state and we don't do a write back into the destination register. Otherwise, we take this path, which leads us down here. And as you can see, we're setting up the source prior, which contains the PC. We're adding it 4 to it, and we're setting up our source into the data register, our write back to the immediate of the ALU, and we're enabling the loading. And that's it. That's about all there is to the JALR. So now let's take a look at some machine code and see where we go. So here we are at the machine code for the JALR instruction, and I've already put it together taken from the bits themselves. I broke them into nibbles and then turned it into hex and placed the hex at the memory address where we'll start executing from based on the reset vector. If everything works according to plan, it should jump all the way down here to this instruction, the load word, and then we'll hit a break. So I've already placed this into RAM, and I've updated the memory file with the name of the RAM file, and we're ready to go. So here we are at the simulation, and let's take a look at what we've got. We've hit the reset over here to the left, and now we're entering into the JLLR state for this instruction, and we can see that we've identified it as the I-type J. There's the instruction, and we begin tearing it down. First of all, we're going to calculate the target address. We take the immediate section of the instruction itself, remember in the data flow diagram, and it comes down into the ALU. Our instruction has X0 as the base register, so we're adding 0 to 2C, and that becomes our target address right here on the PC out. So that's the first half of that instruction, and it looks like it's working great. Excellent. The second half is going to calculate the return address, which hopefully is 08 because the PC prior is sitting at 04. And if we add 04 plus the constant coming out of the MUX, then we get 8, and that is loaded into the X1 register, which is what we had in our instruction in our RAM. And of course, because the target was 2C, it actually found that load word instruction, began loading the word, and eventually it was loaded into the X5 register, which is exactly what we expect. So it hit the right instruction, it jumped to the target, and then finally you can see here it's heading into the black hole. There's the e-break instruction, which is over here to the right side. This jump and link register instruction is doing exactly what we expect it to be doing. Excellent. Now we move on to the store instructions. And as usual, we go back to our data flow diagram to look to see what it is we need to do in order to store some value in the registry file into memory. Now that pretty much says that we need an address and the data that we're going to store. So what do we need to do? What signals need to happen on this diagram? Well, we'll start with the fact that the instruction register has been loaded with our store instruction. And the store instruction uses the RS1, RS2 to indicate where the source of the information is coming from, RS2, and a base address plus an immediate to specify where we're going to store it to. So if we start off with the address part, we'll take RS1, route it through here, and we'll take our immediate from the embedded in the instruction itself, route it through our MUX, through the ALU, and then load it into the ALU out. So now it's ready and presented to memory. We'll also adjust the address source to go along with it. So what about the data? Well, the data is coming straight out of RS2, and it's routed immediately right into the input of our MMU. So that's what we need to control. We need to control the memory write, the memory read, reset source, address source. The instruction is indicating where in the registry file we're working with. We need to set our A and B sources, the ALU operation, and we need to also load the ALU output. So now that we know what signals and muxes to control, we're ready to take a look at the FSM. So here we are back at the FSM, and the first thing we'll do is add a new entry to route us down a new execution path down here. That new execution path, you guessed it, is the store type. And here we can see that the very first state we are going to set up to calculate the address of where we're going to store the data at. To do that, we use RS1 as a base address, and then the embedded immediate value within that instruction, and we add the two of them together. That forms the address. We also do a bit of an optimization here. If we know that if the function 3 says that we're doing a store word, then we don't need to perform this step. We just simply come down here and go immediately into the memory write and disable memory read because we don't want to write and read at the same time. The prefetch is going to bring the read down for us. That's why we're heading out to the prefetch. However, this state is designed to read memory first, because if the opcode function 3 says store a byte or a half word, we want to merge that half word or byte into memory and not overwrite what's in memory. So that's what this extra state does, is it goes and reads the memory, then we execute the storage and merge. The MMU will be doing a lot of this work in here. So there you go, this is the store. Now we head on over to the HDL to implement that store instruction. Again, the first place we start at is our decode. We'll add our new entry, and that'll route us down that new state machine, the ST store. So we'll scroll down here till we get to the ST store, and here we are. The very first thing we do, again, is we set the ALU load to be loaded. We choose RS1 and the immediate. This is going to calculate our destination address. And we select the appropriate address source on that 1 MUX next to the PMMU. And here's our optimization. If we're doing a word size, we can go straight to the memory write. Otherwise, we'll need to go to the next state down here, which we read from memory and maintain our address source. Once we've read from memory, the MMU now contains what it needs in order to go to the write stage, which is to either write straight out or merge that byte or half word. So we keep our source destination maintained. We turn off reading because we don't want reading and writing to occur at the same time, and then we set up for the prefetch. And all the prefetch does is set this back low, but we need it high during this memory write stage. So now that we have the HDL, we're ready to take a look at the machine code for this. And here is our store byte instruction we'll do first. Again, I put it together into its bit form in the field. We have our function 3, which is indicating a byte, our opcode for storing anything, and then the immediate value, which we'll calculate as 0, 1, 0, which is what this is, 0, 1, and then 0. And then our base address is x0, and we're using x14 as the value we're going to store into memory. And if we go to our register file, we preloaded it down here with beef dead. So we expect that the memory location at 10 will eventually have, right here, will have beef dead in it. So I've gone ahead and added that to the RAM file and modified the memory to point to that, and we're ready to run the simulation. This is our simulation for the store instruction. As usual, we have over here to the left our reset, and then we begin fetching the first instruction, which we've now detected as an S-type, a store type, and there's the machine code that we coded up. Excellent. We'll move on to the decode state that determines what the next execution path is, and we can see that it's determined that it's in a store instruction, and so execute will see it as a store. We also increment the PC counter in the decode statement, and sure enough, it's been incremented to 8 from 4. Excellent. So in the first portion of the execution state, we're going to use the ALU to calculate the address to where we're going to store the data at. We can see that the ALU is using the X0 register, the base, plus 10, the immediate, and the answer is 10. And that comes out on the MMU right here. Excellent. This is the address in which we'll store. So here we go to the access. Now because we're doing a store byte, we actually have this state right here. We've entered in, we didn't go straight to the right, we're now in the access portion. So in this state, it's going to take and read from memory simultaneously the ones that are in that memory location, merge the lower byte into it, and then it will be written out because it's being maintained all the way to here. In the write stage, you can see for the very first time in all the instructions we've been looking at so far, the write signal on the MMU has gone low, and when it does, we write that out. Now we don't see the memory location in this diagram. We only see the register files in this diagram. We'll now take a look at the console to see a before and after screenshot. You'll also notice before we do that we have the new prefetch stage. When we've done our write, we now set up for a prefetch, which will then set the memory read low, and that's what we see right here. We see it going low, and of course we go off into the black hole because we've hit the e-break instruction. Here we're looking at the memory as it was before and then after. Before, memory address 4 had all ones in it, and afterwards we had merged in our byte from X14, which had beef dead. The lower byte was AD, and it was merged in at the end of it right here. So it is working as expected. Excellent. Let's take a look at the store word next to see how it bypasses one of the states. So here's our store word. Again, we're going to store the contents of X14, which is beef dead, into this location right here. I put together the bit code fields, then turned them into nibbles and assembled it into the machine code itself and placed it at our vector reset vector start instruction right there. So at the end of this, we should see this location with beef dead in it, the contents of X14. Let's take a look at the simulation. So here's the simulation for the store word, and as expected we see that it's a S-type and that we are executing this machine code. But the biggest thing we want to look at is the fact that we are not doing the store memory access state here. We're now going straight from store to memory write, because we're doing a write and we don't need to do any merging of memory. You see here coming out of memory is our beef dead. We don't have to do anything modifying it. This is the address that we'll write to that we calculated with the ALU, and here the load or the write is being held low, and we write the data beef dead to memory. And we can see right here that it is actually being written to memory right there. Excellent. That's what we expect, and of course we read the next instruction and go off into the black hole as expected. So here we are back at the data flow diagram. We're going to look at the branch type instructions. So again, we have to ask ourselves, what does a control matrix need to do in order to pull off a branch instruction? Well, there's two things it needs to do. It needs to determine whether it needs to take a branch by looking at the ALU flags, and it needs to either load or not load the program counter to take that branch. So we'll back up and look at the instruction register. We know that it actually has the branch instruction in it, which means this is pointing at that instruction, and this is pointing one instruction after it. The instruction itself in the ISA says that we need to branch relative to the instruction itself. So we're using the PC prior. So now we come over to the register file, and we know that the instruction is telling us which two registers to compare against, which means we'll route them through here, we'll activate the subtraction function, and we'll get a results. Now we don't care about what the results is, we just care about the flag, so we'll load those in. Now that's the first state that we've done. Now the second state is we need to calculate the branch address so that in case we do take the branch, we know where we're going. So we'll take PC prior because that's the address of the instruction itself, the branch instruction. We'll take immediate, and we're going to add that to that address. We'll get that value and we'll load it into the ALU out. And at this point, we'll determine whether we're going to do a branch or not. If we do a branch, we're going to take ALU out. It'll have been routed around. We'll activate the load flag, and it'll be loaded into the PC ready for the fetch stage to go and fetch the destination instruction. If we don't take the branch, then we leave the program counter alone and we simply go to the fetch state direct instead of going to a prefetch state, which gives us that extra cycle to load the program counter. So now that we know what to do, how to route our two pieces, we're going to use the ALU twice, once in one clock cycle and then in another clock cycle. We're ready to take a look at the FSM to see what it is we need to do. So here we are at the FSM. We're going to start looking at the branch type instruction to match what we just saw in the data flow diagram. So I'll turn on the branch type, and here you go. We have our first state, which does the calculation of whether we're going to take the branch or not by looking at the RS1 and RS2 registers, which is A and B in our channel. We're going to subtract them. We're also going to load the flags as a result of that into the flags register. Then we'll go to the next state and calculate the branch address. We may not branch, but we're going to calculate it, and that is by taking the address of the instruction itself and adding it to the immediate value that's in that instruction. We'll then test the flags to see whether we're going to take a branch. If we are, then we route ourselves to the prefetch so that we get that extra cycle to load the program counter in. Now, up here in the upper left is that extra cycle, the prefetch. And what it does is it sets up the memory to read the instruction at the branch target. Otherwise, if we don't take the branch, we don't need to go to an extra prefetch stage. We can go straight to the fetch cycle by just bringing down the memory read flag ourselves and going straight into the fetch cycle. Here we are at the HDL code, and as usual we're going to start at the top. We've got our knowledge of the FSM and the data flow diagram. So we'll head on down to the B type. We'll add this new directive in here, this new case statement, and we'll set it to the B type. This will route us down the B-type pathway in the execute phase. We'll come down here to the execute, and here we are at the B-type. So you can see here that we're setting up A and B, and we're going to subtract them and load that flag status into the flags register. We'll use this for the next state, which is the branch state. Come down here and we'll pop that open. And you can see that by default we're calculating the branch address whether we take it or not, which is equal to the prior value, the actual branch instruction itself, and the immediate. And then we have this new thing here where we're looking at function 3 to determine what type of branch instruction we're performing. Are we branching if the two RS1 and RS2 are equal? Are they not equal? One's less than the other, one's greater, less than unsigned, or greater than unsigned? Each one of these, we look at the flags to see whether we take the branch or not. For example, the branch on equal, if the two values were the same in RS1 and RS2, when you subtract them, the Z flag will set because the result was 0. And the inversion for not equal to. Less than is a little bit more complex in that we're looking at the two flags, the negative flag and the overflow flag, to see whether they're different. If they're different, we're going to take a branch. And the greater than is the opposite of that almost, where we're looking to see if they're equal to each other. The less than and the greater than are going to look at the carry flag, and each one is different in that one's inverted from the other. So there you go. This is going to calculate the take branch. So what do we do with that? Well, down here we look to see whether we're taking it. And if we are taking it, we need to load the program counter with the results that was calculated. And we'll need an extra state for that in order to reload the PC. So we'll go to prefetch. Now the prefetch is going to do the memory read for us, but it gives us that extra state. If we don't take the branch, we come down here and we simply do a memory read and then transition into the fetch state, where we'll then go pull the instruction based on what the PC is currently pointing at. So that's the HDL code, and it's probably the more complex of the one based on the fact that we're trying to determine whether we're taking a branch or not. But other than that, it's not that difficult. Now, before we actually go to the machine code and write some things, we need to look at how to form the branch instruction itself. The branch instruction is the first one we're going to look at that does swizzling. That's this right here. The way it works is that in order to form the instruction, you need to calculate, say in this example, what our branch address is going to be. And it's a 12-bit, or in this case a 13-bit value, but we're going to chop off throw the last bit away. But we still calculate it as if it's a 13-bit value. So in this case, we've got the number C as our branch address. So we build the produced value in here, and then we throw off the last bit, which means that our branch instruction is a 2-byte alignment branching address. And then we take the rest of it and we begin swizzling it into the instruction itself. So we'll take, according to the ISA, we take these 4 bits and we route them up into here. we take these 6 bits and route them up all the way over here, and then we take this one whole bit and route it into 7, and the 12th bit over here, or the 13th bit, and route it into the last bit here. This is swizzling. And of course you want it to do the opposite. If you want inside of the processor, it unswizzle those into the immediate. The immediate module that we have will unswizzle these into a produced value again, and then feed that into the ALU. So now that we know about swizzling and how it functions, we're ready to write some machine code. But I'm going to tell you, swizzling bits is tantamount to human error catastrophe. It's almost certain that we're going to mess these bits up as we're swizzling them into the instruction themselves. So let's take a look at a really simple way to do this for us. It's called an assembler, and I've created a one-line assembler. So here we are at the machine code, and the very first thing we need to do before I explain all of this code right here is we want to assemble our branch on equal. This is the one with the swizzling, and we're going to use our assembler. So I'll come over here to the assembler itself, and I'm not going to go too deep into this because this series is about RISC-V, not about assemblers. So in a nutshell, what it does is it runs a regular expression against a single line of assembler that is placed inside of this JSON file. Now I used JSON so that I could provide the context of some of the instructions, and branch equal needs a program counter context and then its target context. So in this case, if I go over to our assembler for the branch type instruction, you can see that there's the regular expression I built, and it breaks it down and pulls it out into the different types of fields, and I print some stuff out for just labeling. And then finally we begin swizzling the produced value into the instruction itself. We set up RS2, RS1, those are the two values we'll compare, the function, which is a branch on equal, which is zeros, and then we finish off the swizzling for the lower half and finally put in the instruction. So let's go ahead and set up our assembler JSON file, assembly JSON file, with the instruction, which I pulled out of here. There's our instruction. I took our program counter and placed it into here, and then finally I took the offset where it potentially may jump to right here, 18, and placed it into one of our labels right here. So now we're ready to run the assembler. Now before I go to this way, I said that the assembler was based off a regular expression, and that's based off of this site right here. You can see that I go ahead and for my expression site, paste in an example of my instruction, and it will then go ahead and break out the fields. And that's what you saw inside of the code here, was the assembler breaking down those fields in the label section right here. So we'll come over to our command line and we're going to run that assembler. So I'll bring that up. We'll come over here and run that. And the last thing my assembler does is actually copies this to the clipboard. So there's our machine code. There's that opcode we saw. Here's our swizzled bits here and here. Here's RS2, RS1, and then there's the branch on equal, which is all zeros. We can come back over to our assembler and paste it in right here, and there it is. So the way this works is we want to test these two registers. If they're equal, we want to branch to the offset, which is right here. So we expect X5 to be loaded with 28 plus C, which is Bob. It shouldn't be loaded with A's, so if it fails to take the branch, it would actually execute this one, which is this value right here. So this is what we're going to do. We'll load X1 with a 5 because this is 0 plus 28, and we'll load X2 with 8 plus 28, which is right here. So now we're ready to run the simulation because I've taken this and copied it into the RAM file and modified the memory module. So let's take a look at the simulation. Here we are in the simulation for the branch type instruction, and this is the program that it's running. We've already gone past the reset sequence, and the very first instruction that we hit is the load instruction for loading in one of the registers. and then we hit the other load instruction, which will load in the second register, the second operand. We move over here. As it's moving along, we finally hit the branch instruction, and this is the main instruction that we're looking at. We can see that it's identified the type, and there's the machine code. So remember, in the control matrix, the B type state will do a subtraction between the two operands so that we can get a flag status. And in this case, because we're doing a branch on equal, we're looking for that Z flag to be a 1. And we know that that has been identified because it went to the BT branch state. And in that state, we turn around and we do an add operation. We add in the PC prior, which is where the program counter is sitting, because it's sitting right on the B type instruction, and there's the program counter right there. And we know that the immediate value is coming from that immediate module, and right there it is, C. You add them two together and we get 18 in hex. And we can see that the program counter has now contains the 18, which means it's when it fetches the next instruction, it's going to find whatever's there, which is, you guessed it, the load instruction. So if we scroll over here, we can see that it has identified it as a load. There's our machine code sitting at 1800 or 18, and already been through the load procedure, but ultimately it's going to load a register, and it's going to load A0A. Now previously I said B, well, I was wrong. It's actually going to this address and loading in this value into the A5. So excellent. The instruction is working. It's doing exactly as we expected to. It's performed both the branch, the B type state, and then the branch state. And then of course it moves on to the next one. So this is working according to our state machine. So let's test the opposite of the branch equal, the branch on not equal. So I went ahead and I changed the BEQ to BNE, reran the one line assembler, put it here, updated the BRAM, updated the memory, and we're good to go. And then I ran the assembler. So in this case, we expected to not take the branch to offset, but to actually fall right through into this instruction and instead load X5 with Bob instead of A0A. So let's see if that happened. So here's the simulation for the branch on not equal. So it's detected that the branch type, excellent. It does the exact same thing. It does a subtraction and the flags do get set. However, we don't take the branch, and we can tell this. We've done the same exact add, but you can see that the PC prior is still 10 and our program counter is still sitting at 10. So we didn't take the branch. Excellent. And you can see that we've immediately gone into the load word instruction at 10, or at the next address, which is 14, and sure enough we've loaded Bob into X5. So that's the difference. The same type of work is going on. It's just that we're now looking for the Z flag to not be set. It is actually set, which means we don't take the branch. And that's exactly what happened. Nice. We've made another large swath through the instruction set, and that finishes off the I type, the B type, and the S type instructions. That doesn't leave much more. As a matter of fact, there are just two of them left. The load upper immediate and the add upper immediate to PC. These are the U types instructions, and they will complete the final ultimate instruction set, the RV32I. So until next time, peace.